Okay, here we go. We're going to quickly go over the homework that was due this Monday and Tuesday on ellipses. So we learned about ellipses last 2 classes ago. I thought it went pretty well. Let's find out. Here we go. It starts pretty easy. This number 9 is kind of the most simple problem you could imagine. The equation is given to you like this. And how I encourage you to think about this is that this is x over 4 squared plus y over 5 squared equals 1. In other words, it's just like a unit circle in which the x-coordinate has been stretched out by a factor of 4 and the y-coordinate has been stretched out by a factor of 5. So this is going to be a vertical ellipse because the circle has been stretched by a larger factor in the y direction. So okay, we just go out here to this point, 0, comma 5, and down here 3, 4, 5 to 0, comma negative 5. The x-coordinate has been stretched out by a factor of 4, and so there are these points 4, comma 0, 0, comma 4, and yeah, there it is, right? This is our ellipse. So, maybe for the sake of not confusing people, I won't even write those points on the board because it's 0, 5 and 0, negative 5 that are the vertices. Okay, so the center is at the origin, the vertices are what they are, and then the only thing left to do is to find the eccentricity and to find the foci. Well, okay, we simply learned that in this case, for this problem, that, well, A is 5, because we always just use the letter A to refer to the semi-major axis, which is 5, and then B is 4, it's just the factor by which the ellipse has been stretched in the other direction, and so in this case, C is just going to be 3. And all right, how do I know this? I know this because first I'll just make a picture. So here is this point here, 0, comma 3. That's one focus, and I claim that the other focus is down here at 0, comma negative 3. And well, why is that? Because there is a theorem that the total length of the string in any ellipse, the constant which defines the ellipse, is just the length of the major axis. And so if that's true, then if you go from one focus, the one at 0, 3, to this point, and then back to the other focus, this must be A. And in this case, my A is just 5. And if this is 5, and this, of course, right here is 4, then that's how we know that that has to be 3. And more generally, this is B, this is C, and this is A in any kind of ellipse. Okay, so good. That was about as easy as it gets. That's kind of the most sort of simple basic sort of problem. All right, so what do we do when it gets more complicated? We just do the same sort of thing over and over. Number 11, this is x squared over 9 plus y squared over 5 equals 1. And this is basically the exact same problem. It's just that now the numbers are a little bit uglier, so let's just see if you are going to kind of panic about that or not. In other words, think of this as x over 3 quantity squared plus y over root 5 quantity squared equals 1. So now we're being stretched out by 3 in the x direction, and we're being stretched out by root 5 in the y direction. So C, therefore, is going to be 2. Because 4 plus 5 is 9. And, well, that's it, right? I now, once again, go to graph this thing, and I see that I'm being stretched out by 3 in the x direction. So this right here is 3, comma 0. This is negative 3, comma 0. And then we have our y-coordinate, which is root 5 is like basically a tiny bit more than 2. So here's 1, 2, 1, 2, and we're sort of up here or something like that. And well, now I will just make my ellipse. Okay, and what else were we supposed to do? Oh, eccentricity is C over A. I forgot about that. So this is 3/5, and the eccentricity in an ellipse is always going to be, since the eccentricity is C over A, then C is always less than A in an ellipse, of course, because the distance from the center to a focus is always less than the distance from the center to a vertex. So the eccentricity for an ellipse will always be less than 1. Good. So for this problem, what is the eccentricity? C over A. So it's just 2/3. I calculated that C is 2. Therefore, my focus is going to be right here at 2, 0, and over here at -2, 0. And I guess that's it, right? I got my vertices, I got my foci, I got my eccentricity, I graphed it. That's pretty much all there is to it. Okay, so these were just like, very easy, basically. Let's do one that's a little bit harder. Is it even harder? Let's find out. Number 19. Well, it's a little bit harder because there's some algebra to do. So let's go. 9x squared plus 4y squared plus 36x minus 24y plus 36 equals 0. Okay, so strategy, analyze this ellipse by converting it into a form in which I can recognize it and understand it geometrically. Alright, let's go. We will collect all of the x terms together, and we will collect all the y terms together, and we will move the negative, we'll move the 36 over to the other side. Okay, writing a little bit small here because I don't have a lot of room. I'm factoring out a 9, so that's x squared plus 4x. And then here I shall factor out a 4. That becomes y squared minus 6y equals -36. And now I'm just going to complete the square separately in both variables, being very careful as I go. What am I doing here? Well, I need that to be a 4, but by writing a 4 here, 9 times 4 is 36, so what I've actually just done is to add 36 to the left-hand side, so I need to add 36 to the right-hand side as well to balance it out. And okay, that's just a 9 and to complete the square, so I also added 36 again, 4 times 9, so I have to add 36 again. Okay, so this one is also working out about as smoothly as it can go, because this is 9x plus 2 squared plus 4y minus 3 squared equals 36. And now if I just divide by 36, then I get x plus 2 squared over 4 plus y minus 3 squared over 9 equals 1. And so I did the job, right? I have completed the square and expressed this this equation in a form in which I can now understand it. And okay, so what's going on? Well, first of all, the center has been shifted. It's not going to be at the origin. Instead, it's going to be at -2, 3. So because of boom, boom. And then also, this is going to be a horizontal ellipse because I'm being stretched in the y direction by a factor of 3. A is 3 and b is 2. And okay, while I'm at it, I will compute c. C is going to be something like root 5, I guess, right? Because in any ellipse, as we already saw, b squared plus c squared is a squared. So 9 minus 4 is 5, so c is going to be root 5. Okay, let's just graph this. Eccentricity will be c over a, so root 5 over 3. Let's try to squeeze in a picture here. We are going to go to the point -2, 3. So boom, 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 cha-cha-cha. And that's my center. And then what else do I have to do? Well, I'm being stretched out by 3 in the y direction. So 1, 2, 3. So I have my other, one of my vertices is going to be at -2, 6. And my other vertex is going to be here at negative 2, 0. And then my x-coordinate is being stretched out by a factor of 2. So I got a little point here, and I got a little point here. And my ellipse itself is going to look, therefore, something like that. It's pretty terrible, but there it is. Maybe I just kind of erase that. So my vertices are at negative 2, 6 and negative 2, 0. I hope this is right. I think it should be. So I wrote horizontal, but I meant vertical, and in fact the answer is vertical. Okay, so I don't know what I was thinking there. Of course this is going to be a vertical ellipse, because we're stretching out by 3 in the y direction and 2 in the x direction. So I thought about it correctly, but I said and I think wrote the wrong word. Let me just double check now and make sure I'm not being stupid. Negative 2, 3 is my center, stretching out by 3 in the y direction, by 2 in the x direction. So yeah, I think we're looking good here. Okay, what's left to do? I got my eccentricity, I have my vertices. I guess I just need to find the foci and plot them. Well, I know that c is root 5, so I know that the foci must be root 5 away from the center along the major axis. And so we're going to have one focus like here and one focus like here. And the coordinates of that focus are going to be, I go back 2, and then I go up 3, and then an additional root 5. And this one is going to be negative 2, comma 3 minus root 5. So it's a visual exercise, in my opinion, to you can do some of that in your head, I guess, but it's nice to draw it out. At least you're imagining this kind of picture. Okay, we're still on the level of just like basic stuff. This is just everyone in America does this kind of thing when they learn ellipses. Okay, let's keep going. I think there's 1 or 2 more that are just basically like this. So it's just algebra practice, getting used to the formulas and understanding the relationships. And then there's some more problems that involve kind of more thinking a little bit later. Yeah. Okay, 27. Let's go. 27. X squared plus 2y squared minus 3x plus 4y plus 0.25. Alright, that is pretty annoying. X squared plus 2y squared minus 3x plus 4y plus a quarter equals 0. Okay, so this is a good example of a problem in which the numbers get annoying. So what are you going to do when the numbers are annoying? Don't cry. It's going to be okay. We can do it. So, let's go. The strategy is exactly the same. We just have to possibly deal with some fractions and stuff. So this is x squared minus 3x. Here we collect the y terms together, and then we'll subtract 1/4 over to the other side. Or we'll subtract 1/4 from both sides. Okay, so far so good. I just see that there are going to be some fractions. So this is 2y squared plus 2y equals negative 1/4. And then just you know, half of 3 is 3 halves. And so I just have to add 9/4 here in order to complete the square. Yeah, that's just true. And if I add 9/4 to the left-hand side, then I have to add 9/4 to the right-hand side. Here, this number needs to be 1 to complete the square, so I just added 2, so I just add another 2. Okay, so maybe this isn't so bad. I know one of these, I can't remember which it is, the numbers are gross, but maybe this isn't the one. This is x minus 3 halves squared plus 2 times y plus 1 squared. And what do I get over on the other side here? I get 4, right? 8/4, so that's 2 plus 2, so I get 4 over here. Alright, and now I suppose I need to divide by 4. So I guess these numbers are a little bit gross. This is x minus 3 halves squared over 4 plus y plus 1 squared over 2 equals 1. Okay, so this wasn't so like hard or anything, but it's just kind of annoying because I now have some gross numbers that I need to deal with. I'm just checking myself so I don't do anything, wrong. I know what I'm doing, but it would be a shame to have sort of bad math. But I think that's completely correct. Okay, well, what does this tell me? It tells me that I have an ellipse. It tells me that the center of this ellipse is going to be at 3/2, -1. That's fine. It seems as if it's going to be horizontal. This time I really do mean horizontal because I'm being stretched out in the x direction by a factor of 2. A is 2, and I'm being stretched out in the y direction by a factor of √2. So, finally, what is C is also just going to be √2. Because they have this Pythagorean relationship. Alright, so maybe we just go do it right now, right? Here we go. We're going to go over 3.5, or rather 3/2, and down -1, so that's already kind of annoying. 3/2, -1, but then I have to get stretched out by a factor of 2 in the x direction, so my vertices are going to be 2 away horizontally from 3/2, -1, so they are going to be at 7/2, -1, so 3.5. So that's one of my vertices, 7/2, -1, and the other one is going to be at -1/2, -1. Okay, and what about the y direction? Well, we're being stretched out by a factor of 2, which is about 1.4, so that's also kind of annoying, and we're got something like that. Alright, so if I did this correctly, and I think I did, it's something like this. Chop. The eccentricity is going to be C over A, so that's √2/2. And, and that's my ellipse. And, let's see, what else? Are we supposed to do? I guess we're supposed to find the foci. Where are the foci √2 away from this point? So there's going to be one that's maybe here-ish. And what is that point going to be? Ugh. It's going to be 3/2 plus √2, -1. And there'll be another one that's here, I guess? Yeah. And that will be 3/2 minus √2, -1, and I think that's all I got. I think that's all I need to be talking about there. Vertices, 7/2, -1, and -1/2, -1. Foci. This was just. That's it, man. There's nothing to talk about here. Okay, I think that ends was that the end, or is there more? I think that ends the just to do a lot of algebra section of the homework, and now we're going to do a bunch of sort of, I would call them thinking problems, in the sense that they are shorter, and there's more sort of, maybe understanding involved, but still pretty easy. So 30, what do we know? What are we told? We're told that the vertices are at plus or minus 6, 0. I'm just copying directly from the problem. And the foci are at 0, plus or minus 4. Vertices at plus or minus 6, 0. Foci at 0, plus or minus 4. This is number 30. So it's literally the way you do this is you just make a picture. I'm sort of perplexed by this slightly. That's because I copied this problem down wrong. Okay, third try. 30. Vertices are at 0, plus or minus 8. Foci are at 0, plus or minus 4. Yeah, there we go. Okay, so now this is looking a lot simpler. So we have, well, I won't even try to make it accurate. I have 4, and I have 8, and I have 4, and I have 8. And yeah, I mean that's it, right? Without even getting into trying to make this accurate, because I think that I don't really care about it being accurate. This is generally the picture. This is quite ugly picture I've just drawn. But anyway, this is enough for me to visualize what's going on. What is going on? I have a horizontal ellipse. The average, the midpoint of the foci is of course the origin, so this is going to be centered at the origin. It's going to be horizontal, and it is horizontal. A is 8, and C is 4. And if A is 8 and C is 4, then, can I do this in my head? Let's see, 64 minus 16 is 48, I guess. And so B squared, I'll even just say B squared is 48. Because in this ellipse, maybe just worth it kind of drawing this all one more time. This is C, the distance from the center to a focus. This is B, which I just set out to calculate moments ago. But this is A. Half the length of the string and equal to the length of the semi-major axis. So keeping this kind of basic picture in mind all the time, B squared plus C squared is A squared, so in fact it's 48 and 16, which is 64, so there it is. Alright, so what's the equation of this thing? Well, it's going to be x over, x has been stretched out by a factor of 8, so this is going to be x squared over 64 plus y squared over 48 equals 1, and that's really just all there is to that problem. Good, 31. 31 is another just sort of thinking, reading, comprehension, drawing a quick picture, figuring out kind of problem. Here we're told that the vertices are 0, plus or minus 2, and the minor axis has length 2. Okay, well if the minor axis has length 2, being kind of careful there, that means that B has to be 1. The semi-minor axis has to be 1. And if the vertices are plus or minus 2, then that means that A is 2. Okay, so drawing a picture of this, it's going to look not quite like that. It's going to look more like this. So the vertices are here at 0, 2, and 0, negative 2. The minor axis is 1, and so we got something that looks like that, basically. Pretty straightforward. Again, the average of the vertices is the origin, so this thing is going to be centered at the origin. And all I have to do is figure out what C is. What's C? If A is 2 and B is 1, then C is going to be root 3. And I'm not even sure I needed to say what that was. I think the problem just says find the equation. Yeah, so I mean this is just a piece of cake. This is going to be x squared over, make sure I'm not doing anything stupid, 0, 2, 0, yeah, x squared over, over 1, if that makes you feel better, you can write it like that, plus y squared over 4 equals 1. So we're just stretching things out by a factor of 2 in the y direction only. Okay, just do a quick time check. Yeah, I guess we're doing alright. Alright, that was 31. Moving right along to some more of these. 34. Yeah. This is just kind of more of the same, I guess. My vertices are at 0, plus or minus 5. And so-called solution point, okay, that's not really a standard piece of terminology, but it's just their awkward way of saying this is one of the points on the ellipse. Okay, so this is not so hard. Once again, just like for all these problems, the thing to do is to just make a picture. So let's do that. What do I have here? An ellipse with vertices with one vertex here and one vertex here, and it's going to be some kind of vertical ellipse, of course, because the vertices are aligned vertically. So let me just put the point in. The point that I'm being told is on this ellipse is 4, 2. So okay, I'm not trying to be super accurate or anything here. That's terrible. Alright, art skills, just terrible. Okay, well anyway, there it is 4, 2. Okay, well how are we going to figure out the equation of this ellipse from just this information? Well, if I didn't tell you about this point 4, 2 at all, what would you do? I guess you would just observe that A is 5 and that B is, unknown. So if A is 5 and B is unknown, then let's just write down what we think the equation of this thing is. It's going to be x squared over b squared plus y squared over 25 equals 1. Because it's an ellipse centered at the origin, I know that because the vertices are symmetric with respect to the origin, which has been stretched out by 5 in the y direction, and b is unknown. The length of the minor axis, the semi-minor axis, is unknown. So that's what I know. And well, then if you tell me that this ellipse goes through the point 4, 2, then the thing to do is to just plug 4, 2 into this equation and work backwards to find b. So that's just all we do. Plugging 4 in for x gives me 16 over b squared plus 4 over 25 equals 1. And now I just have a single equation that I need to solve in one variable b, and then that will be the end of it. Okay, so moving over here, I want to kind of squeeze this in. Let's see, what do we get? Well, we get 16 over b squared equals 1 minus 4 25ths is 21 25ths. And okay, this is a little bit interesting. If you cross multiply, you get 21b squared equals 400. So apparently b squared is 400 over 21. That's just the right answer. It's just kind of a weird problem, I guess. And alright, if that's the case, then the final answer here is x squared over 400 over 21. And I probably would just write it like that, sort of intentionally, plus y squared over 25 equals 1. So that was kind of a strange final answer there, but I think the logic of it, I think, was pretty clear. What was that number, 34? I guess if I'm being responsible, I should check these as I go, but I'm pretty much positive that's right because I've done this problem before, and so there it is. Well, that's interesting. What number did I just do? 34? Oh, sorry, it was on the wrong section. 34. Yeah, there it is. Great. Okay, good. 5 more to go. I'm doing almost every problem, not every single one. I think 35 and 36 are both kind of easy, so let's just do those right now. 35 says, hey, the center is now not the origin. The center is now the point 3, 2. Okay, making me jump through some hoops there. A is 3C. That's slightly interesting. And the foci are at 1, 2, and 5, 2. The foci are at 1, 2, and 5, 2. Well, always the thing to do is to make a picture. So I make a picture over here. 3, 2, boom, that's my center. Where are the foci again? They're at 1, 2, and 5, 2. Therefore, this distance is just 2, and therefore C is just 2. And by the way, if C is 2, then A is just 6, and then there's really just not much to this problem then, because I just need to go 3, 2, and then over 6, so that'll be at 3, 8. There'll be 1 vertex, and the other vertex will be 6 away from 3, 2 in the other direction. So that'll be 3 comma negative 4. So there it is, 3 comma negative 4. And once I know that C is 2 and A is 6, then I can tell you what B is. B is going to be 36 minus 4 is 32. So B squared will be 32. I guess that's right. Yeah. And so B is going to be, whatever it is. Whatever that is, I guess that root 32 is kind of like 4 root 2. But maybe it's even easier to just leave it as root 32. What is the square root of 32? It's going to be more than 5, less than 6. So I guess this number is about, I don't know, 5.6 maybe, something like that. Who knows? 5.7? Okay, why is that important? It isn't really important, because I just know it's going to be up here and over here, and alright, that's enough for me to graph this thing, and I do think it's worth sort of taking it out there to the end. So what is the equation then of this thing? Well, it's going to be x minus 3 squared over something plus y minus 2 squared over something equals 1. And I'm being stretched out in the x direction by a factor of 6. So that's 36. And this we said was 32. So that's the answer there. Okay, good. 36. What's up with number 36? I lost my spot. There we go. The vertices are at, this problem's also not that hard. Vertices are at plus or minus 5 comma 0. And the eccentricity is 3/5. Okay, well, I think that for this, we just do it, right? Let's just do this pretty fast. If the vertices are plus or minus 5, then dude, that just means A is 5. What does this thing look like? I don't know, something like that. But if A is 5 and eccentricity is just C over A, then this just means that 3/5, the eccentricity, has to be C over 5. So this is just kind of a silly way of telling you that C is 3. And if C is 3 and A is 5, then that means that B is 4. And this is actually just the simplest ellipse imaginable. It's x squared over 25 plus y squared over 16 equals 1. Okay, so good. Hopefully this was like, roughly the right amount of homework for you. Who knows if that's true? Oh man, 43. Okay, there's kind of one more boring problem, and then there's sort of 2 cool ones. So 43 says, kind of planning out my white space a little bit. 43 says to use facts about the lattice rectum. And this is something that I derived in the page 7 of the Ellipse packet, which for some classes, got a certain version of this, but then later on after class I decided this needed to be significantly edited, so I produced an edited copy, and I told you to take a look at the answer key. But there is a problem in the textbook which walks you through this explanation, but maybe I didn't assign it because I thought it was unnecessary. What is the actual problem? The problem is 9x squared plus, okay, 9, I guess I'll just do this whole thing. 9x squared plus 4y squared equals 36. And, okay, the question is, making use of the lattice rectum. Who knows what that means? That's very vague. So I will interpret that as like find the length of the lattice rectum and like draw it and stuff like that. Okay, well first let's put this in standard form. So if you divide by 36, you get x squared over 4 plus y squared over 9 equals 1. Okay, great. Now what? Well, I can make a picture of this, and alright, it's going to be an ellipse with major axis 6, minor axis 4. So there it is. Great. What else is going on? Well, A is 3, B is 2. What's C? Well, C is going to be root 5. Because B squared plus C squared is A squared. Well, great. What's root 5? You know, it's a little bit more than 2. 2.2, something like that. So it's going to be over here. There's going to be this point 0, comma, root 5. And there's this other point, 0, comma, negative root 5. And arguably, I can make a more accurate ellipse. This one's so small, it doesn't really matter. I can make a more accurate ellipse if I know this segment. Let me just erase that. If I know what this segment is right here. Sha. And what is that segment? It's a chord of the ellipse, which is perpendicular to the major axis through the focus. So, like I was saying, this point is 0, comma, root 5. And what are these little points here? Well, I don't know. All I can say for sure is that they have height root 5. Okay, so if you didn't know anything about this whatsoever, you could just do some math and you could just say, I wonder what this point right there is. That dot, that red dot. Well, it's going to be something, comma, root 5. So I don't know, pick your favorite letter, like, M or something, M, comma, root 5. And now, what do I know about this point, M, comma, root 5? I know that it is on the ellipse. So it must satisfy the definition of the ellipse. So I suppose I can just calculate, what M is by plugging it into the formula. And that's just exactly what we do. We plug it in here, and we get M squared over 4 plus root 5 squared, so 5/9 equals 1. And maybe it was even easier to plug it into the original equation, but okay, too late. So I get M squared over 4 equals 1 minus 5/9 is 4/9, and therefore M squared is 16/9. And if M squared is 16/9, then M is 4/3, and that's about all I need to know for this problem. Therefore, this point is 4/3, and this chord by symmetry must be negative 4/3, comma, root 5. And there's not just one lattice rectum for an ellipse, there are two. The other one is going to be down here, and of course it's going to have the same type of points. This will be 4/3, comma, root 5, and this will be negative 4/3, comma, negative root 5. Okay, well, great. So this problem is now just done, and I guess the only thing that you might want to do, if you didn't want to keep doing this over and over again, is to have a general formula. And so if you wanted a general formula, then you would just repeat these exact same steps, but now in general. So now you would have this point 0, comma, C, and you would again have the lattice rectum, which is this chord, and you would again try to find this point, and you could call it temporarily M, comma, C, wondering what that little M thing was, and then you would just do some algebra. What is the equation of this generic vertical ellipse? It's going to be x squared over b squared plus y squared over a squared equals 1. And if I just plug in this generic point M, comma, C, well, it's not a generic point. If I plug in this point M, comma, C, which I know must be on the ellipse, then I can figure out what M is. So if I plug M in for x, I get M squared over b squared plus, for y, I plug in C, and I get C squared over a squared equals 1. Okay, so that becomes M squared over b squared equals, subtracting gives me 1 minus C squared over a squared. And then I can get a common denominator here on the right, so that's a squared minus C squared over a squared. But then a squared minus c squared is just b squared. And so I get m squared over b squared equals b squared over a squared. showing a lot of steps here. So m squared is b to the fourth over a squared, and m is thus b squared over a. So if you're into formulas, this is now a formula, b squared over a, which will tell you half the length of the lattice rectum. Okay. Good. Man, 2 more problems to go. Let's just do them. These are slightly interesting. These are all about orbits. Okay. And yeah, one of the reasons to study the conic sections are that for reasons which are sort of intuitive, but the details are kind of difficult, because we are operating in our macroscopic world under mainly under the influence of gravity, which is an inverse square force, then a lot of things in our world happen like quadratically, and all objects moving around the sun follow orbits which are conic sections. And so, as we've already discussed, you could imagine an object moving around the sun in a circle, but a circle is kind of like a very, 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 very special case of an ellipse. So there's sort of like somehow like a 0% chance or something that the orbit around the sun would be exactly a circle. It's probably going to be off a little bit, in which case it will be an ellipse. Another option is that you could have a parabolic orbit, and that's also extremely unlikely because a parabola is just a special case, sort of on the border between ellipse and hyperbola. Could you have a hyperbolic orbit? Yes, but then you wouldn't really call that an orbit. That would just be an object which was hurtling towards the sun, and with such speed that it slingshots around the sun and shoots off forever and never comes back. An object following an orbit like that, or a path like that with respect to the sun, would be an object that we would say would be under a hyperbolic orbit. But most of the common objects that we are familiar with, because we see them again and again, like the planets themselves and other things like asteroids and stuff and comets, are following elliptical orbits. Alright, so the part that is not totally obvious is that, and I'll draw this, I guess I'll draw this the same way that, well, maybe I won't draw it the way the book does. I'll draw an ellipse, and this ellipse has 2 foci, say, I don't know, here and here or something like that, and the sun will be at one focus. And, okay, really when I say the sun, I mean like the center of the sun, because for various reasons which are, again, not totally obvious, but in fact this is true, that you can act as if the entire mass of the sun is concentrated at a point at the center, as long as the, actually even if it's not, well, assuming it's equally dense all around or symmetrical sort of with respect to itself, then you can definitely do that. But okay, this is the path that objects will take around the sun. Objects which are orbiting around the sun, say like a comet or something like that, will follow some elliptical orbit, and specifically an elliptical orbit in which the sun is at one focus of that ellipse. Okay, and if you have some comet, I don't know, Halley's Comet or something like that, which is a period, has a period of something like 80 years or something, then it spends the vast majority of its orbit, very, very far out, far away from the sun, and then gets close enough to the sun and hence close enough for us to observe it, 1 year out of 80, and then goes back again. So that would be a satellite with a very high eccentricity. Yeah, because remember that eccentricity is c over a, and in this case, if this were c and this were a, if the foci are very, very far, yeah, I guess maybe the best way to put it is, if the ellipse is very stretched out, then it means that the foci are going to be very, very close to the vertices. And if that's true, then the difference between C and A is only going to be like a little bit less than 1. This is kind of like very elliptical, you might say. Alright, and then the flip side of this is if the foci are very, very close together, then C is very, very small. And in that case, the eccentricity will be close to 0. And the actual path of the Earth, for example, around the Sun is elliptical, but it's an ellipse which is indistinguishable from a circle. I believe the eccentricity of the Earth is something like 0.001 or something like that. It's so small, it's so close to being circular, and this is why it took thousands of years for people to recognize that the Earth's path around the Sun was an ellipse and not a perfect circle, because it's so close. That what you can imagine if you try to draw sort of an accurate picture of the Earth's path around the Sun, what you would have is that the foci are just literally almost on top of each other. And so now you have this kind of, they're sort of almost acting as if there's just one focus kind of at the center. It's indistinguishable basically from a circle. So close are if you plot the ellipse, which is the Earth's orbit around the Sun, the foci are so close together that in fact one focus is at the center of the Sun and the other focus of the ellipse is inside the Sun. So it's close to the edge of the Sun. Okay, that's some science facts. Let's do this problem now. So I will use this picture, which is slightly different from the picture that the book had, but I think is better or something, simpler. And of course I've drawn this, wildly not to scale because it just makes it easier to see. But in fact, the orbits of all the planets are pretty close to eccentricity 0. Okay, without further ado, oh, by the way, there is also some other bit of vocab which they teach you here, which is the Perihelion and the Aphelion. I believe I'm pronouncing this correctly. The Perihelion is the smallest distance of an object to the Sun. So this is called the Perihelion, is this distance here. So this is the Perihelion. So for an object in orbit, it's the moment in the object's orbit when it is closest to the object it is orbiting around. And then there is the Aphelion. I hope I'm saying that correctly, which is going to be over here. So that's going to be this. This is the Aphelion. Okay, good. Well, that was came up in a previous problem, actually number 45, a problem that you did, but I don't really feel like going over that problem. Let's just do 47 and 48 and call it a day. What is 47? This refers to Saturn. Saturn moves in an elliptical orbit with the Sun at one of the foci. The smallest distance and the greatest distance of the planet from the Sun are blah 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 blah. Find the eccentricity of the orbit. Okay, so basically there's not a lot of math going on in this problem. What you have to realize is that if this point is at, I guess, negative C comma 0, say, and that's C comma 0, and that's A comma 0, I mean this seems even a little bit silly to write all this, but the entire major axis has length 2a, and so basically when you add up the perihelion and the aphelion you get the major axis. So that's kind of one thing, right? That P, I'll just say, well, I probably shouldn't say P and A, I'll just say like perihelion plus aphelion is just 2a, the length of the major axis. But also, maybe sort of more to the point, that's not so helpful. What is more helpful is that the perihelion is in fact just A minus C. And the aphelion is just the rest. It's just A plus C, I suppose. Is that just true? Yeah, that's just true. So A plus C. And therefore, the way to get the length of the major axis is to just add these two. So it's actually just, it's exactly what I said above. I take it back. That was helpful. But this is sort of also useful. Okay, so in this problem they give me these, terrible numbers. I'm supposed to do something with these terrible numbers. 1.3495 and 1.5 0.045, just disgusting, times 10 to the 9th kilometers. Alright, well if you're still watching this video now, I guess I'm just going to do this. What do I get? 0, carry the 1, so that's 14, 5, 8, 2. That wasn't too bad. So, what do I know? I know that 2.854 is the length of the major axis, and therefore A is just going to be half of that, so that's 1.4, half of 54 is 29. No. Half of 54 is 27. Chop. So A must be 1.427 times 10 to the 9th, and what's C? Therefore, well, I use like this one, right? I just now subtract, yeah. So this was the perihelion, and this was the aphelion. So once I know A, I can just subtract A from the aphelion to get C. Yeah. So I just do 1.5045 minus 1.427, and that should give me C, I guess, right? Am I doing this right? I'm kind of doubting myself for a second, but yeah, I think it's good. So okay, what do I get? This kind of sucks. 9 minus 2, 7. So 0.0775 times 10 to the 9th is my answer for C, if I'm doing all this math right. And therefore the eccentricity of Saturn, I'm expecting it to be pretty small. It's going to be 0.0775 over 1.427. And so if I'm doing that correctly, that's like about 1/20th. So I'm just going to eyeball this, that the eccentricity is about 0.05. And I suppose I have an answer key here, right? So my answer key says that the answer to number 47 is, yeah, it's all just exactly right. Every single thing I wrote there is exactly right. Possibly some arithmetic errors here and there, but anyway, the gist of the numbers is completely correct. So I might have done some subtraction wrong. Did I do some subtraction wrong? 1.5045. I don't know. That was good enough. 1.5045 minus 1.427. It's a little bit embarrassing if I did my subtraction wrong. Borrow 4, 10, 9 minus 2, 7. Oh, should that be a 1? No, I think it's right. I don't know. Okay, good. That was number 47. And now we get to number 48. The last problem from this homework. Hopefully they don't have any numbers here. Yeah, good. Phew. If the apogee and the perigee... Wait a second. Is that just the same thing as... Is apogee and perigee just the same thing as aphelion and... Now I'm doubting myself. Alright, quality of this video is dropping a little bit, but greatest and least distances from the Earth's center to the Moon's center. I do not understand the difference between apogee, perigee, aphelion, and perihelion. It's possible that helios is the root word sun, so I suppose perihelion specifically refers to the closest distance to the sun. Yeah, that's just got to be right. And aphelion refers to the farthest distance of some object to the sun. But now, this problem number 48 is asking me for something involving the Earth and an Earth satellite, say the Moon. So that's actually kind of annoying. I don't think I realized that right now, that we had two separate words for the exact same mathematical sort of physical concept, but now I'll draw, okay, I can't draw the Earth, so I'll just draw like, Earth, and here are some continents and stuff like that, and it just looks like a bad smiley face, and okay, great, so that's one focus, and then we have some object orbiting around the Earth, and so now the concept is, just add some blue oceans and stuff like that in there. Yeah, that's looking good now. Okay, But the perihelion is, no, but it's not called perihelion now, it's called perigee. Perigee. The perigee is now G like geo, like Earth. It's the closest point that an object orbiting the Earth is to the Earth, and apogee is the farthest point that an object orbiting the Earth is from the Earth. And, okay, but the logic of everything we did over here is exactly the same. And now, instead of using numbers, thankfully, we just have to prove some little formula. And the formula is, you know, let this be, let this be big A, and let this be big P, and basically find a formula for the eccentricity. Okay, well, I think it's pretty clear that if I add P and A, then I get, you know, I get 2A. In other words, the apogee plus the perigee is the length of the major axis. But then, as we said before, that's a fact. And another little fact is that what is the perigee? Well, the perigee is just A minus C. And the apogee is just A plus C. Okay, so if that's true, then maybe what I need to do here is, well, I basically have two choices, right? I can add and I can subtract these two equations. So if I add these two equations, then I get that A plus P is 2A, which is what I just said above from just by duh. But if I instead take the two equations and subtract them, then I get A minus P equals C minus negative C is 2C. And therefore, if the eccentricity is C over A, I might as well write it as 2C over 2A. And 2C is A minus P, and 2A is A plus P. So that is exactly the formula that they asked me to prove. In other words, this is a formula for the eccentricity of an object orbiting around the Earth, but expressed in terms of the apogee and the perigee of that object. Okay, good. That was maybe a lot slower than it needed to be, but I did thoroughly go over all the ellipse problems. You're going to hand these in tomorrow, and then you're going to have a nice break. Goodbye.